So as I was preparing to do this video, I realized that this whole time that I think I wrote it down wrong one time for agcl. I looked in your book. The KSP isn't 1.8 times 10 to the minus 7 like I keep writing in your notes. It's 1.8 times 10 to the minus 10. So we're just going to pretend like all those other KSPs I was doing were at a different temperature. Think about that. At any rate, we're going to talk about dissolving precipitates right now. And you take something like silver chloride here, and it's not very soluble. In fact, with its new and revised KSP, it's especially not soluble. So if that's true, what we're talking about is, well, then how can we get it to dissolve? And sometimes it's about picking the right stuff to dissolve it into. So I'm going to do a little example problem here. And that example is we're going to calculate the molar solubility of agcl in 1 molar ammonia solution. And this is something that's going to actually help agcl to dissolve better because, and here's where we're going to put it together with what we started the chapter, it turns out that ammonia likes to be a ligand for silver. So here's the reaction that I am providing for you. Silver chloride reacts with ammonia to produce a complex ion in a Lewis acid-based way. Here, these ammonia come in as a ligand onto the silver. We get chloride ion. And some pieces of information that are helpful now in the book, in your blues, you'll have to look these up out of the table. But that's a solid, and it has a KSP associated with it. The new revised one, I'm going to use for this particular one. And this diamine silver ion, you don't have to name it, don't worry, has a KF, or formation equilibrium constant here, of 1.5 times 10 to the 7th. It's large because it's a complex ion. And we need to find the molar solubility. Now, this is an equilibrium here. So we need to find the KEQ value for this in order to help us do the problem. But these guys are going to help us. So let's take a look, and we're going to go ahead and write, silver chloride. I'm just going to write the equation associated with that KSP. So it breaks apart into its ions. These are aqueous. And our KSP for this reaction is 1.8 times 10 to the minus 10. And then I'm going to go ahead and do it for this one. We're going to produce this silver with the ammonia ligands. And so that's produced by a silver ion plus 2 ammonias. And these are aqueous as well. All of this is aqueous. And this K of formation is, as I told you, 1.5 times 10 to the 7th. So here's where this comes into play. Because it turns out in this, since we have 2 equilibria, and everything here, if you look, matches up to something. Now, the silver doesn't, but that's going to cancel out, if you notice. Here we've got, the complex ion, the chloride, the silver chloride. So if we add these 2 reactions together, the silver ions cancel, and we end up with agcl plus 2 ammonia yields the complex ion and the chloride ion, which is exactly what we want. And remember, we've done this in an old chapter. If you add these 2 reactions together, you multiply the K values. So our KEQ will be the KSP times the KF, which when you multiply those, you get 3.1 times 10 to the minus 3. Now we have enough information to find the molar solubility. So our KEQ for that reaction, if I just write the expression, will be the complex ion times the chloride ion. AgCl is a solid, not including it, but the ammonia is aqueous, so NH3 squared because of that coefficient. And now we can go ahead and do an ice table. we'll do that in molarity. Not going to do silver chloride here. We're starting with 1 molar ammonia. If you go back to the original problem, that's where we were. Let's say we had none of this to start. Now we're going to lose some and gain some. So we'll gain S, lose 2 S because of this coefficient. So this becomes 1 minus 2S, S and S, and we can plug that in to our original equilibrium expression. So S squared over 1 minus 2S is equal to our new equilibrium constant here. And when you solve for that, S is 0.00, no, I got carried away, apologize, 0.050 molar. So this is the molar solubility of AgCl in that ammonia solution, which is a greater molar solubility than we did it in water, even if we had used the correct value. It's definitely more soluble in ammonia. It dissolves better, and it dissolves better because it forms this complex ion with this very large Kf value. A side note, just because I don't want people to get confused here, is if we were to look at some reaction, say X3Y2 solid, and it breaks apart into 3X2 pluses and 2Y3 minuses, and you're given the KSP as some value, and you were to do the ice table, we're not going to do it for the solid, and this becomes 0 and this is 0, and you gain 3S and you gain 2S, and so this becomes 3S and 2S. But when you are asked the question, what is the molar solubility? It's always just S, not 2S, not 3S, because if we were to think about it, you're starting with 1 mole of this. And as it dissolves, let's say there's some number here, X, as it dissolves, this is literally losing 1 S. So when we talk about molar solubility, it's really how many moles of this stuff dissolve per liter. And since this always starts with a 1 in front, that's why it's always S. So just something to consider in that case. All right, last thing I want to do on this video is I want us to just sort of talk about, in general, dissolving precipitates. So if you have magnesium hydroxide, a solid, and when it dissolves, albeit only a tiny bit, it produces this equilibrium. So here's your beaker of water, you've got a big chunk of magnesium hydroxide on the bottom, and a tiny bit of magnesium that is supposed to be a 2. Pretend it's a 2 plus and some OH minuses, but not a whole lot because this is pretty insoluble. In fact, its KSP is 6 times 10 to the minus 12, so we don't have very much ions. But we're trying to see, how do I get the solid to dissolve? And so as we look at this, there may be some things to consider, like probably you could raise the temperature, because generally solids become more soluble as you raise the temperature. Think about iced tea versus hot tea probability. That's not what it's supposed to say, probably. As you raise the temperature, more sugar dissolves in your tea. So if you raise the temperature, you're probably going to be able to get this to dissolve better, because most solids are actually endothermic reactions. I say probably because there's like 1 or 2 that aren't, and you would need the delta H value to know that. So as long as the delta H for that is a positive value, raising the temperature will help. You could add more water. Well, why? Because if you add more water, you will essentially decrease these concentrations. If you decrease those concentrations, Le Chatelier would say it's going to try to increase it by shifting it right. If it shifts right, the solid dissolves. One more thing, and you might want to just pause and think if you could think of it, is what else could we do to change these? And another possibility is you could add or increase the concentration of hydrogen ion. Add some acid to it. Now think about why that is. Because if you add H+, it will react with OH- to form water. Well, what does that do? It decreases the hydroxide ion concentration. And in doing that, it's going to cause it to shift right. So those are all ways we can get a solid to dissolve that isn't dissolving well. I'm going to compare it to one other thing, very similar, zinc hydroxide. And the thing that's going to change here is that zinc is a transition metal. Now, consider where we started and what transition metals could do. So I put some zinc hydroxide in some water. I don't know what the zinc hydroxide KSP is, but this is insoluble, so we know it must be fairly small. So that means that we've got some zinc ions and some hydroxide ions, but not a lot. And so if I ask the question, how can I get it to dissolve? All those same things, all above, apply. We could raise the temperature. That will probably help. We could add more water to decrease these concentrations. That would probably help. We could add an acid to decrease this concentration. That would probably help. But this is a transition metal. So an additional one that you could do is to add a ligand to produce a complex ion. So if that's a possibility, you could do that. So for example, like in the one we've done before, you could react it with some ammonias. Now at this point you may not know what that complex ion will look like, but you could look in a KF table and find one. And there's a KF associated with that, which are usually really, really big. So think about what that's happening. If this is really big, so this shifts far to the right, it's going to grab onto any zinc ions. Well, we go back to this reaction. If the zinc ions are getting reduced because, the zinc ions are getting reduced because they're turning into this stuff. If this goes down, this is going to be causing it to shift to the right, which will cause more of this solid to dissolve. All right, that's enough of that. We'll chat in class.